Hi everyone, I'm Eun-Noan and I'm a graduate student from Yonsei University, and I'm really happy to be here to share my works, and I'm going to talk about weak lensing analysis of emerging galaxy cluster and how the merger history of this cluster could be reconstructed. So galaxy cluster mergers are the most energetic events since the Big Bang, so we often call them as natural particle accelerators, where we can constrain some of the fundamental physics. However, observations provide only a single snapshot of the few gigayears of the cluster merger. And among merging clusters, some exhibit diffuse radio emission in the cluster outskirts, which are known as radio relics. So radio relics are known to trace merger-driven shocks, and the video shows a very simple visualization of how radio relics are formed. So after the two clusters collide, the merger shocks are generated, which are denoted as the red color. And these merger shocks accelerate thermal ICM to the relativistic speed, and those relativistic electrons emit synchrotron radiation in the radio frequencies. So to say it in short, those radio relics are the merger shocks observed in radio frequencies. And even if the observation provides only a single snapshot of the merger, if we can observe those two double radio relics in the cluster outskirts as they trace the same merger event, the merger history can be well reconstructed using these double radio relics. Okay, now move on to the let's move on to today's target. The name is the PSD2G and some numbers at redshift 0.23. So this image shows a optical color image taken by hyperspring cam. And first, as you can see, there are two distinct BCGs, one in the northern and the other one in the southern. And the X-ray emission shows an elongated morphology between those two BCGs. And what makes this cluster so special is those two very bright, large, and very widely separated double radio relics, which are located equidistant from the cluster center. So this chart shows a scaled relative separation, which is a relative separation divided by R500 of the cluster of all known double radio relic clusters. And as you can see, our target has the largest scaled relative separation, which means that the 2.7 megaparsec of the physical separation is very large, considering its lower mass. So if the collider has lower mass, then the collision velocity would be lower, which leads to the slower shock speed. So even with the slower shock speed, the separation between the two relics are very large. So we thought that this cluster is in an extremely late phase of the merger. Okay, then why we need to focus on the late phase of the merger? Well, there could be several answers to this question, but I would like to focus on the dark matter properties. So if dark matter particles experience other kinds of interactions other than gravity, for example, like a self-interaction among dark matter particles shown in this middle panel. By the way, this is not from the simulation, it's a simple visualization from Python, so please keep in mind. But anyway, if dark matter experiences self-interaction other than gravity, the halo separation would differ from what we expect from the CDM collisions, and the difference in halo separation gets larger for the late phase of the merger. So what I want to say here is that the late phase merger could be a very useful astrophysical laboratory to constrain the dark matter properties. So to understand this cluster merger as a whole, we initiated a multi-wavelength project of this cluster, including the X-ray and the radio and weak lensing analysis, and all of those works are published in APJ in early this year. So from the radio analysis, those two diffuse radio sources are confirmed as radio relics based on the spectral and polarization analysis. And from the X-ray analysis, we have found that the morphology of X-ray emission shows very disturbed morphology, and also we have identified several X-ray discontinuities, which might indicate that this cluster has undergone a very complex merger dynamics. However, as you know, the mass of the galaxy clusters are dominated by the dark matter. So the dark matter distribution is a key factor in determining the merger dynamics. And how can we reconstruct the dark matter distribution The answer is weak gravity lensing analysis, because weak lensing directly proves the projected mass distribution. So to conduct a weak lensing analysis of this cluster, we observed this cluster using Subaru and hyperstrand cam in G and R2 band. And this right figure shows a color magnitude diagram of the entire. So after identifying a spectroscopic confirmed member from the SDSS catalog, we selected background galaxies whose magnitudes are greater than the cluster vesicles and also bluer than the vesicle. And after applying some quality criteria for the shape fitting, our final source density is about 40 galaxies per icon square, which is quite large number considering the boundaries observations. Okay, so this figure shows a projected mass distribution of the entire field. Okay, so as you can see, we have identified several overdensities, including some background clusters, and our target cluster is PSE, and some numbers is detected as the most highest significance in the center of the field. If we zoom in the central region, then we can clearly see that the mass distribution of this cluster is composed of the two subclusters, one in the northern and the other one in the southern. And the physical separation between those two subclusters is about 500 kiloparsec, which is much smaller than the radius separation. And again, this indicates that this cluster is in a late phase of the merger. Okay, so now we have reconstructed the projected mass map of this cluster. Then let's compare it with other cluster components, such as the galaxy number density and the galaxy luminosity map observed in R band, and the gas distribution traced by the X-ray emission, and finally with the BCGs. So as you can see, first there are two symmetric radio relics, and all of the cluster components, including the mass, galaxies, and gas and BCGs, are all showing a bimodal distribution. So we assume that this cluster merger is primarily driven by the two main subclusters, one in the northern, the other one in the southern. So we model this cluster merger as a two-component model. Okay, so for the mass estimation, we positioned two NFW halos, each centered at the northern and southern BCGs. And assuming the empty relation and epsilon running into chains, we have estimated that the mass of the cluster for the northern and the southern in terms of M200 is about 0.9 and 2.7 times 10^14 solar masses. So we have found that this cluster has undergone a major merger of mass ratio of 3:1. So before we move on to the merger scenario reconstruction, I would like to summarize the key observational features that could be used for the simulation. First one is the relic-to-relic separation, which increases over time, as I mentioned before. And the other one is the halo-to-halo, 500 kiloparsec per halo-to-halo separation, which oscillates over time until they merge into a single halo. So those two separations can give us the timing constraints of the merger. And also we have estimated the masses of each subcluster, and so thanks to the weak lensing analysis, those two subcluster masses can be the initial conditions for the simulations. Okay, so we ran the ideal simulation using the Mantis code, of course assuming the weak lensing mass estimates. And this figure shows the reference free-fall line with 0 input parameter. So in this figure, the x-axis shows the time since the per-center passage, and the y-axis shows separation, and the blue line is for the halo separation, and the red line is for the sharp separation. So as you can see in this reference free-fall collision, halo separation reaches the observed separation at the time since per-center passage about 0.8 gigayears. But however, at this moment, the separation between the two sharps for the two relic is only about 2.0 megaparsec, which is about smaller than the observed relic separation. So we thought that since the speed of the relic or the relic, the separation evolution of the shock is primarily determined by the masses. We thought that the halo separation should reach 500 kiloparsec a little bit later to reproduce the observed halo and shock separation simultaneously. So our best matching configuration is an off-axis collision, and in this configuration, the halo separation reaches about 500 kiloparsec at the time space passage of about 0.9 gigayear, and at that moment, the radial separation is also shows the same the observed shock separation. And for the last part, I would like to firstly mention about the future direction of this thing. As I mentioned before, this cluster is a late phase of the merger, which could be used to constrain the dark matter properties. However, there are quite a lot of uncertainties remaining. For example, we don't know the viewing angle of the merger, or we don't know the impact parameter of the merger. So to constrain the dark matter properties, we need a lot of samples, and we need to conduct a statistical analysis. So we are waiting for the Rubin and SKA era, where we can detect a lot of radio-related clusters and conduct weakness analysis of them. And the next one is to be the new insight to the particle acceleration. So if I overplot the clusters R200 in this image, then you can see that those two radio relics are located around the clusters R200, where the intra-cluster median density is very low. So those two relics are still bright in radio, so maybe we need some alternative explanation of the shock acceleration mechanism other than just traditional diffusive shock acceleration. So this slide is a summary slide, and I'm going to stop my presentation here, and thank you for listening.